So here's another video on statics, i.e. equilibrium, and it's to do with ladders. So there's a ladder resting on rough horizontal ground, leaning against a smooth vertical wall. As ever, what are the sources of forces? Well, straight away the ladder has a mass, so we put the weight on. The ladder is in contact with the ground, so there will be a normal reaction at point A. The ground is rough, therefore there will be some friction. Now let's just consider what might happen. If this ladder was to slide, we might expect that the base of the ladder would slide away from the wall. So the inclination of the ladder is to move to the left as we're looking. Therefore, we would anticipate friction acting in the opposite direction to oppose that motion. Now the ladder is in contact with the wall, so straight away there's a normal contact force. The normal contact force being at 90 degrees to the wall. And because the wall is smooth, there's no friction at B. So once you've set up your force diagram, we now use equilibrium to find any missing forces. And equilibrium in this situation means two things. One is forces in any direction cancel out. And therefore, in this case, forces to the right equal forces to the left. So the friction at A will equal the normal reaction at B. And vertically, weight must equal the normal reaction at A. But also, equilibrium means that if we take moments about any point, that will result in a zero moment. So let's apply that to the situation here where we've got a 15 kilogram ladder resting against a smooth vertical wall and it's placed on rough horizontal ground. Horizontally, we've got the friction at A equaling the reaction force at B, and vertically we've got the weight of the ladder equaling the reaction force at A. Now, if we take moments about point A, that's probably a good thing to do because if we take moments about point A, we won't have a moment from the friction. Why? Because the friction passes through point A and the force that passes through a point cannot have a moment about that point. And similarly, the reaction force at A passes through point A, so that will also have zero moment. So the only two forces that will have a moment about A are the weight of the ladder and the normal reaction at B. Now, the 15G force provides a clockwise moment. If we pull downwards, we'd expect rotation clockwise about point A. And the reaction force at B will provide an anti-clockwise moment, and those two moments must cancel each other out. So, the clockwise moment from the weight of the ladder, well, that's the line of action of the force. So we want the perpendicular from this line of action which passes through point A, which would be this distance where the red blob is across to point A, that perpendicular distance from the line of action. So that distance there is 2 cos 70. So the moment provided by the weight of the ladder is 15G times 2 cos 70. Now the reaction force at B, there's the line of action of the reaction force. The perpendicular distance from that line down to point A, well, that's the blue dotted line you can see there, and that distance is 4 sine 70. Therefore, the moment provided by the reaction force at B is R of B times 4 sine 70. Those two moments equal each other, they cancel each other out, giving us a reaction force at B of 26.751, and that will mean the reaction force at A, which equals the friction at A, which equals the reaction force at B, is 26.8 newtons to 3 significant figures. To find mu, the coefficient of friction, there's limiting equilibrium. It tells us that in the question. So friction is at its maximum. So friction equals mu times the normal reaction. So this friction at A down here will equal mu times that normal reaction. The normal reaction we know is 15G. So we have that frictional force, 26.751, note we don't round off, equals mu times the normal reaction, divided by 15G, gives us a value of mu, which is 0.182. Now, let us assume now a person of mass m kilograms stands on the ladder 3 meters up from the base, so that's where that person's weight is marked on. And remember, in equilibrium, forces in any direction cancel out, so horizontally we have that, and vertically we have that. And if we take moments about any point, it results in a zero moment. So there is a person up the ladder. And those are our, when we resolve horizontally and vertically, those are the equations that we obtain. Just pause the video for a moment just to make sure that makes total sense to you. If we take moments about A again, the weight of the ladder and the force exerted by the man on the ladder will both provide a clockwise moment, and the reaction force at B still provides an anti-clockwise moment. So, once again, the line of action and the perpendicular distance is 2 cos 70, so that moment is 15G times 2 cos 70. For the 75G force, that's the line of action, that's the perpendicular distance, and that's 3 cos 70, so that's 75G times 3 cos 70. And the reaction force at B, there's its line of action, there's its perpendicular distance, and it's R of B times 4 sine 70. The anti-clockwise and clockwise moments cancel each other out, and that gives us a normal reaction force at B of 227 newtons, roughly, and that equals the frictional force at A. Okay, so therefore, for friction to be maintained, that would need a force of, equilibrium to be maintained, that would require a frictional force of 227 newtons. As it says there, that was nearly 10 times the previous answer with somebody on a ladder. And now to finish off this particular question, we wanted to find mu. Assuming limiting equilibrium, the frictional force at A will be at its maximum. Dividing therefore by 90G, we end up with mu equals 0.258. So I hope that makes sense to you. In terms of ladders, we resolve horizontally, we resolve vertically, and we can take moments about any point. And the best point to take moments about is when you've got some unknowns. Take moments about that point, because the unknowns are eliminated because they don't have a moment if they pass through that point.